We call this a complex if any composition of a pair of these functions in a row is zero. And we said it's exact at AN. If kernel Fn plus one is the image of Fn. So what it meant to be a complex was this was contained in this. And if you get it equality, it's called exact. So for example, so here's, sometimes you see people do this kind of fancy terminology, sometimes, or fancy notation. This is exact if and only if F is 1 to 1, right? Because obviously the image of this map is 0, right? And so for it to be exact at A, it means that the image of this, which is 0, has to be the kernel of this. So F is 1 to 1. Is exact if and only if G is onto, because the image of this, well, the kernel of this is all of C, right? Because this is the 0 map, because there's nowhere to go other than 0. So that means the image of this, to be exact here, the image of G has to be exactly C. What does this mean? Right. So the image of this, which is 0, has to be the kernel of this. So F has to be 1 to 1. And the image of this has to be the kernel of this. Well, the kernel of this is B. So that means the image of F has to be all of B. So F is both 1 to 1 and onto. And now let's make things a little bit more interesting. An exact sequence what am I going to call this? This is definition 12. An exact sequence form 0, A, B, C, 0, I'm going to call it F and G, is called a short exact sequence. Why short, you might say? Because after all, I do have some exact sequences over here that are shorter. But notice an exact sequence of this form is boring because this just means that A is isomorphic to B. In a certain sense, this is the shortest exact sequence that you can have where something interesting might happen. And actually, short exact sequences are very important in the sense. So this seems sort of arbitrary, call this a short exact sequence, but there's more justification because in a certain sense, this is the DNA that makes up every exact sequence, no matter what. What I mean by that is you can obtain any exact sequence on planet Earth by splicing together short exact sequences. So these are the building blocks, and I'll show you how the weaving goes in a moment. But let's let me make an observation here. if is a short exact sequence, then number one, and this characterizes it in certain sense. What does it mean by F? Well, it means that F is 1 to 1. It also means the G is onto, correct? Because the kernel of this, which is all C, should be the image of G. So that takes care of exactness here, and exactness here, and exactness in the middle just means that the image of F is the kernel of G. So those three things are bread and butter. They characterize this being a short exact sequence. Let me let's look at some examples, then I'm gonna do some splicing. Example. How about this one? I like this. Let me get this here. Let's let F and I'll let G. So I'm going to let this first. Of course, here I've got a particularly easy module because I've got Z module, so these are just a billion groups. Z to Z, I'm just going to do multiplication by this fixed n. So any input K, your output is NK. To make this exact, can anybody tell me what the map G has to do? So my input G is some integer M. What do I do to make this go to Z mod NZ? How about just take it to its coset that you're identifying with, right? This is just an objection math. This is sometimes called, right, where pi n of m is m bar mod n. Okay. Okay, so let's test this. I think we would all have to agree that since n is a natural number, that this is 1 to 1, because if nk is equal to 0, then k must be 0, right? So no problem there. And this last g is clearly onto, isn't it? Right? Because given any coset here, n plus nz, it comes from n, right? Everybody okay with that? Composing two in a row certainly gives you that this is a complex, right? Because if you start here with k, you go to nk, and nk mod n is just 0 bar, right? So 2 in a row gives you 0. Right? What is the kernel of G? Well, what goes to this is just the kernel of G is just multiples of n, right? And this is equal to the image of F. So this is a good example of a short exact sequence. Here's one. Here's a really, and this one is a model for many important examples of short exact sequences. A, C, B, R modules. Then by the way, this isn't the only way to make this a short exact sequence, but I'm going to do what comes naturally to me. I'm going to call this inclusion into A, injection into C. Here's the way this works. Inclusion A takes A to A comma 0, and projection to C takes the order pair AC to C. Notice that inclusion of A is certainly 1-1. It's sort of the identity on the first coordinate, isn't it? I agree with that. So this is certainly 1-1. The projection is certainly onto, because if you have an arbitrary C in C, then 0 comma C goes to C. No problem there. What happens if I compose 2 in a row? Well, you start with A, you get A comma 0, and then you project that 0. Okay, so if I compose 2 in a row, A0. What about the other containment? I need to show that everything in the kernel is in the image. So what does it mean? Kernel of pi C is the set of A comma 0, where A is in A. Everybody agree with that? Because really what it means, you're in the kernel if and only if that second coordinate is 0, right? And what is this? This is exactly the image of out A. Okay.
How is that if you're only covering like the A's and not the values of like A plus?
This doesn't have to be onto, and this doesn't have to be 1-to-1.
Okay.
Here's another example that you can generalize. I'm going to do a specific example because I'm a lazy man, but I've reconciled that with myself. So this one can't work like this example. Can somebody explain why? Because notice what happens in my in kind of generalized example that I had over here. Notice that the middle was the direct sum of the bookends. Is that the case here? No, it is not the case here, right? Because if you take the direct sum of the bookends, every element's order 2, right? 1, 0, 0, 1, they're all order 2. Whereas this thing has an element of order 4, so they're not the same. Nonetheless, there is a short exact sequence here. Let's it'll help me to write down the elements to do this. So I'm going to write Z2 this way. And to distinguish it, I'm gonna write Z4 this way. Where the bars mean mod 2 and the stars mean mod 4. Now, this is actually helpful because, let me call this F and G. Actually, this is kind of helpful because there's only one one-to-one map from my Z2 and Z4. And oh, and look, let me steal your thunder for you, because if this is going to be a homomorphism, I know for sure that's got to happen. We're going to take the identity to the identity. Where does one bar go? Well, actually, there's two places it could go. One of them is to the identity, but I don't want that, right? Because I want F to be one-to-one, right? And so that would suck for me. So where can I send one bar besides the identity? Two star. Because one is an element of order 2, I can send this to 2 star. And notice that the subgroup of Z4 that corresponds to 0 star and 2 star is isomorphic to this subgroup of 2, right? And there's F. 0 star, 1 star, 2 star, 4 star. Money play fun. 3 star, that is, sir. 0 bar, 1 bar. How does G work? Well, once again, and of course this has to be onto. Where does everything else go? It's mod by 2. That's essentially what you're doing. You go mod 2. So you dump these two onto 1 bar and 0 bar, 2 bar on 0 bar, right? Everybody okay with that? And that's really the only way to make an onto homomorphism from that group to that group, right? Let's check this out. Certainly F is 1-to-1, right? I mean, I can look at that and tell. And certainly G is onto. Now, when you compose F and G, certainly that goes to 0 and this goes to 0. So the composition is 0. And notice the kernel of G zero star, 2 star, which is the image of F. So this is a rather different, if you will, in Texas. Yes.
Why'd you send it to 2 instead of like 1?
You can't send it to 1 or 3. And the reason is this is of order 2, agreed, over in the original. This sucker's of order 4. And when you have a group homomorphism, when you take an element of order n, it has to go to an element of order that divides it. It can't go to a bigger one. Okay, other questions? Let's generalize this example. This is another reason that short exact sequences are so important. If I give you a general homomorphism of bar modules, I can use that to build a short exact sequence. So oh, actually, before I all think of that, let me get this here. Okay, so I'm gonna talk about. So I'm gonna augment this and give you a definition. Uh, Yeah, um. Let's, let, so here's another example. Let phi from M to N be an Riemann homomorphism. Okay, suppose that I've just got any Riemann homomorphism that I want. I can sort of encode this information into a short exact sequence. Notice that the kernel of phi is a submodule of M, agreed? So would everybody agree that, okay, so what I'm doing is I'm kind of building my R module or my short exact sequence as I go. So I've got my garden variety homomorphism in N. The kernel of phi is a submodule of M, right? Now, I want to finish this. I'm making this short exact sequence. I've already got that this is one-to-one because it's a sub. Where should I go from here to here? Anybody see? What's that?
The image of phi, so that it's onto.
Yes. But you're too smart for me. So let me do this. Because I am a simple creature. Right? So this is just projection, right? So notice that I've set this up to make this is one-to-one. This is onto, right? Because I mean, this is I of X equals X in M, and pi of M equals this coset. Right? This is set up to be a short exact sequence. This is one-to-one. This is clearly onto, right? And notice when I compose, X is in the kernel of phi, so this projection here kills it, right? And on the other hand, this projection here, what is the kernel of this map? It's all the stuff in kernel of phi, which is the image of this. Do I agree with that? But he said something about the image of phi. Why is he right?
Function is always onto its end.
Well, this is the first isomorphism. I notice that. So we can note image everybody okay with that? So I made some remark about so in other words, this sort of underscores short exact sequences because basically short exact sequences show off the important parts of your homomorphism, your M, your kernel, your image, right? I did say that if you have a long exact sequence or an arbitrary exact sequence, you can splice these together using. I'm gonna demonstrate why that's true because sometimes I give this as a homework problem, but frankly, I don't want to read this crap. So suppose we have suppose that this is, I'll call this Fn, Fn plus one. Suppose exact. Let's pray that I do this right. So I'm doing it on the board for the first time. Oops. Okay, so where I'm assuming that these black F's that go across is exact, so the image of this is the kernel of this, so forth, so on. Right? Notice that, given this AN, the kernel of Fn plus one is in there, so it's a submodule. And the image of Fn plus one, so you get this exact sequence going this way. Do I agree with that? This is exactly what we had here, right? Do I agree with that? Now, because of exactness, this is equal to the kernel of Fn plus two. Everybody agree with that? And this one is equal to the image of Fn. Well, thinking of this no longer as the image of Fn plus one, but as the kernel of Fn plus two, this goes into here, and this goes into the image of Fn plus two, right? Right. And by the same token, if I think of this, instead of the kernel of Fn plus one as the image of Fn, this is, let's see, this should be the image tail. This is the kernel of Fn. And right. So you can think of Fn as, notice this is the what notation I use. This is inclusion, projection, inclusion, prime, projection, prime, inclusion, double prime, projection, double prime. So in other words, you can think of Fn as this composition here. In fact, it's easy to check that when you do this projection here and this here, you get exactly what Fn is, because this projects to this image point, which goes to here. So you can easily see that these things can be spliced together by these separate short exact sequences. So all the blue diagonal ones are these short exact sequences that you can use to splice together this thing by short exact sequence, short exact sequence, short exact sequence, shortcut them across, and you get these exact sequences. Okay. So short exact sequences are the breakdown of a single homomorphism. You might consider that, and you can use that to splice together any exact sequence that you want. So they're very, very useful. So they're the atoms, if you will. Okay. Any questions? I'm gonna leave this next one. I'm gonna do an easier one because hey, that's me. I'm gonna do something more. Here's a general proposition. I'm probably gonna ask you to prove at least one of the statements from this. This is called the phi lemma. Consider, let's see, X, G's, H's. Proposition 1244 is called phi lemma. Consider the following diagram of our modular homomorphism with exact rows. Commutative diagram. Of our modular homomorphisms. With exact rows. So we have F1, F2, F3, F4, each one, H2, H4, G1, G2, G3, G4. Okay, so these are all our module homomorphisms. The diagram is commutative. What does that mean? That means if you start anywhere on this little puzzle piece, A2, and you follow maps, if you go in another direction and end up in the same spot, you get the same answer. So in other words, doing this composition is the same thing. That's what the commutative diagram means. And these are all our module homomorphisms. What can we conclude? Oh, did I say exact rows? That is. If G2 and G4 are onto G2 and G4 are onto, and G5 is 1 of 1, then G3 is 1 of 1. Nope, on. So in other words, if these are onto and this one's 1 to 1, then middle guy is onto. There's a dual result. If G2 and G4 are 1 to 1 and G1 is onto, then G3 is 1 to 1. So if these two animals are 1 to 1 and this one is onto, the middle one is 1. That's kind of amazing, right? Because these ostensibly these could be anything, but the exactness of the rows and the commutativity of the diagram gives you this. I'm going to let you prove one of those, probably. I am going to give you a corollary to this, and I'm going to prove the corollary because it will give you the spirit. Because proving these kind of diagram case theorems are, well, it's more fun than you can have with markers on a whiteboard. It's great. It's great. less fun with pencil and paper, but let's. Here's the corollary that I promised. This is called short file lemma. Uh, Corollary. Well, consider following. Community diagram. Of our module homomorphisms. With exact rules. This is just like the five lemma, only it's short five. Well, more. 0, V1. Two, H1, H2, G1, G2. So here's the statement of it. If G1 and G3 are onto, then G2 is onto. B, if G1, G3 are 1 to 1, then G2 is 1 to 1. And of course, we cannot resist the observation G1 and G3 are isomorphisms. And so is G2. Let me make a couple of observations. I'm gonna prove at least part of this for you. The first observation is this immediately follows from the five lemma, if you've got that, because the missing maps here go from 0 to 0, and of course are trivially both 1 to 1 and onto. So if you apply the five lemma here, you immediately get this. And of course, part C follows immediately from parts A and B. Everybody okay? So I'm going to prove this in the raw, just to kind of give you a feeling for how this proof goes. And these proofs, this technique is called diagram chase. So we have 0, A1, A2, A3. I'm going to talk through most of the details, and this is why this is really a lot of fun to do on a whiteboard, and maybe less so to actually write down on a piece of paper. So I'm going to record facts as I go. Okay, so let's prove A. I'm going to use support. Everybody got anything on this board? Okay, so let's look at A. suppose G1 and G3 are one. Okay. Let's let A2, actually, let me call it X. Let's distinguish it. So I've got some X here, right? What do I know? I know it's in the kernel of G2, right? And I want to prove that, of course, I want to prove that this is 0, but all I know at this juncture is it goes to B2. Right, that's the best I can do. Right. Now, let's do some pushing, right? Where does B2 go? Well, I mean, I can't push back here, but I can push in the direction here. This goes to B3. Everybody agree with that? Oh, already lost my mind here. I do know something here. What did I say X was? It was in the kernel of G2. It goes to 0 here. Right? Much better. Certainly what I wrote was true before, but not very helpful. So I don't know much, but I know it. Let's push on to 0 here, because these are homomorphisms. So if I follow X here, it's 0, so it's got to go to 0 there. Agree? Now X goes this way over here to A3. Perhaps. That's the best I can do there. Where does A3 go? It's got to go to 0. If I push A3 down here, it's got to go to 0 by commutativity of the diagram, right? So let me record some of this stuff. G2 of X is 0. So G2 H2 of X is 0. And this should equal F2 G3 of X. So what do I know? I know that F2X is in the kernel of G3 because it goes to 0 this way. And what, pray tell, is the kernel of G3? 0, because G3 is 1 to 1. This is 0. Therefore, F2X is equal to 0. So X is in the kernel of F2. Everybody agree? But what is the kernel of F2? Can you tell me exactly what it is? It is the image of F1. So I don't know much, but I do know that there is something, say A1, that goes to X. Hence, there exists A1 and capital A1 such that F1 A1 is equal to X. Now let's chase this A1 around and see what happens to it. A1 goes somewhere, B1 say. Well, where does B1 go? Well, the diagram's commuted, right? A1 by this route goes to 0. So it has to go to 0 here. So since doing F1 G2, this is the same thing as doing G1 H1. Therefore, G1A1 is in the kernel of H1. And what is the kernel of H1? Well, remember, this is 1 to 1, so the kernel of H1 is 0. Do I agree with that? I agree. Everybody with me? So that means that B1 is 0. Therefore, A1 is in the kernel of G1. Right? Well, the kernel of G1 is also 0. Because G1 is 1 to 1. So A1 is 0. Right? Therefore, X, which by definition is F1 of A1, is equal to 0. So G2 is 1 to 1. Everybody okay with that? Yes.
I kind of lost track after finding A1. Like at that point,
Okay, so you're good with A1 goes to X.
yeah,
Okay. Well, follow A1 this way. B1. Since A1 to X to 0, B1 has to go to 0 because the diagram has to commute.
still B1 is in the kernel.
B1's in the kernel of this map, but this map is 1 to 1, so B1 is 0.
And it's 1 to 1 because it's exact.
Because of exactness of this row. This map is 1 to 1 by definition.
Sure.
So that makes that 0,
Which means
which means X is 0. Right. Everybody okay with that? I'm going to chase the other direction without the symbol, see if you guys can piece it together. We'll do it the other way. Now let's suppose so now suppose that these two are on 2, and again the rows are exact. Suppose I've got some Y here. I have to find something here that goes here, right? So let's start chasing again. Y goes to B3. I agree with you. And I don't know much, but I do know that that last map that G3 is onto, right? So there's an A3 that goes to B3 because of the fact this is onto, right? This is onto. So there's an A2 that goes here. Everybody agree with that? Oh, I'm so tempted, am I? To say A2 goes to Y, but I can't. It just goes to some B2 here. But I do know something about B2, and what's that?
B2 to go to B3.
B2 must go to B3, right? Because A2 goes here, A2 goes to A3 to B3, A2 goes here, and I don't know much, but it has to go to B3. Now I seem stuck, but there's an important detail. Notice this is a homomorphism, and H2 of Y equals H2 of B3. Right? So H2 of Y minus B3 is 0. That's that homomorphism problem, right? So y minus b3 goes to 0 here. So there's a b1 that goes here because of exactness here. Now, this is on 2. So there's an a1 that goes here. A1 goes here to here. So when I follow it this way, this goes to some x that goes to y minus b3. Gotta have that because the diagram. That is to say, G2 of x is y minus b3. Notice that G2 of A2 this shouldn't be a B3. I'm on correct. That's a B2. Right. This goes y minus B2. G2 of A2 goes to B2. So G2 of x plus A2 is y. And so it's not 2. These things were a lot of fun, so you might play around with this. Yes.
Can you do the like first, or can you show like the first 3 arrows from Y to like the first 3 arrows from Y to wherever you went? I just-
Oh, there is no error. So y goes to B3 just because it can. And this is on. By the way, I know we've run over a little bit. If you got to go, you're not hurting my feelings. That's cool. Y goes to B3.
Mhm.
This is on 2, so A3 goes to B3.
Uh-huh.
This is on 2, so A2 goes to A3, which goes down here.
Okay.
Now A2 goes down here, but I don't at this point know it goes to Y.
Mhm.
But I do know that whatever this goes to the same thing Y does, right? And that's where I got this thing, Y minus B2 is the kernel. So there's something that goes to that. I pull that back and the X plus A2 does what I want. The X part goes to this, the A2 part goes to this, add them up and I get Y.
Okay.
Other questions? All right, you all have fun with this and we will see you next time.